Okay, so we are going to continue sketching a graph without using a calculator. We are going to use our curve sketching abilities. And the first thing that we find is the domain. So we have a polynomial. That means our domain is all real numbers. So negative infinity to positive infinity. The next thing we need to find is the in behavior. And in a polynomial, we have those 4 different options. So we have degree of 4 and a positive leading coefficient. So what does that mean our in behavior is? It means it will point upwards in both directions up to positive infinity. Okay, the next thing that we want to find is the y-intercept. So how do we find the y-intercept? We plug in x equals 0, and if I plug in x equals 0 to this function, I get negative 24. And then the x-intercept, that's the last bit of information I can get from the original function. So I get 2 x-intercepts in this graph. What are they? So from the first factor, I get an x-intercept of 2, 0. And from the second factor, I get an x-intercept of negative 3, 0. Okay, this is all the information we can get from the original function. Now I have to find the first derivative in order to figure out where our function is increasing, decreasing, if it has any maximums and where those are at, and if it has any minimums and where those are at. So to find my first derivative, I have to use a product rule. Bring down the 3x minus 2 quantity squared. And I would multiply by the derivative of the inside for a chain rule, but that's 1, so that really doesn't change anything. And then the derivative of the other piece is 1. So to find the first derivative, I am going to cross multiply. So I get 3 times x minus 2 squared times x plus 3 plus x minus 2 to the third. Okay, and then we have looked at how to handle derivatives such as this. The worst thing that we could do is multiply it all out, because that would be a lot of extra work for us. What we want to do is continue to factor it. So if I look at both factors, what do they have in common? They have an x minus 2 squared. So I will take that out. And in the first piece, I have the 3, and I have the x plus 3, this x plus 3 left. So if I multiply those together, I get 3x plus 9. And in the second piece, I had a degree of 3, and I only took out 2, so that means I have 1 copy of the x minus 2 left. So if I simplify this, I get the quantity of x minus 2 squared times 4x plus 7. Okay, now I need to find my critical numbers. And how do I find critical numbers? Well, this function is defined everywhere, this derivative is, so I don't get any critical numbers from that. But I get 2 critical numbers when I find out where my derivative is 0. One at positive 2, one at negative 7/4. So my fence posts, I will have 2. One will be at negative 7/4. The other will be at positive 2. So now let me test something in that first interval. Let's test negative 2. And what do I do with negative 2? So if I plug it in the derivative, my first piece, the x minus 2 squared, that's actually always going to be positive. If I plug it into the 4x plus 7, I get a negative. Since this is the first derivative, negative means my function is decreasing. In the next interval, if I plug in x equals 0, I get a positive, which means my function is increasing. And then in the last interval, if I plug in 3, I get a positive, which means my function is increasing. So we are decreasing, then increasing, and then increasing some more. So my interval where my function is increasing, I can write as negative 7/4 to infinity. I'm combining the 2 intervals because our function is defined at 2. my function is decreasing from negative infinity to negative 7/4. And then how do I determine if I have a maximum? Well, my derivative doesn't change from plus to minus. My function never goes from increasing to decreasing, so that means I have none, no maximums. How do I determine if I have a minimum? That's if my function goes from decreasing to increasing, or my derivative goes from negative to positive, and I do have one at negative 7/4. So now negative 7/4 is going to be a point on the graph. To find the y value, I will take the negative 7/4, plug it into the original, and that will give me negative 66 if I round. Okay, so this is all the information I can get from my derivative, increasing, decreasing, max, and min. The other things I need to know before I sketch is where's my derivative concave up, concave down, and do I have any inflection points? So to figure that out, I need to use my second derivative. So let me rewrite the first derivative. F prime equals x minus 2 squared times 4x plus 7. And I'm going to take the derivative of this by doing another product rule. So I get 2 times x minus 2, and then that'll be 4. So f double prime, I will cross multiply. I will get 2 times x minus 2 times 4x plus 7 plus 4 times x minus 2 squared. And then I'm going to do the same thing. I want to factor this. I don't want to multiply it all out. So what do they have in common? Well, they have a 2 and an x minus 2. And from my first piece, that leaves a 4x plus 7. From my second piece, that's going to leave a 2 and another x minus 2, and if I multiply those, I get 2x minus 4. So simplifying that, I get 2 times x minus 2 times 6x plus 3. So what will be my fence posts in my second derivative test? I'll get one at negative 1/2 and one at positive 2. Okay, now let's pick something in this first interval, let's say negative 1, and we plug that into our second derivative, and what do we get? Looks like we're going to get a negative times a negative, so that will be positive. Since it's the second derivative, that means my graph is concave up. In my next interval, let's pick x equals 0, and if I plug that into my second derivative, I get a negative, which means my graph is concave down. And in my third interval, I plug in, let's try x equals 3, and if I do that, that's positive, so my graph is concave up. So the intervals where my graph is concave up will be negative infinity to a negative 1/2, union 2 to positive infinity, concave down between minus 1/2 and 2, and then an inflection point is where concavity changes. So I'm going to have one at negative 1/2, and I have to figure out what the y value is, so let me plug that in really quick. Let's see, we want to take the negative 1/2 and we want to plug it into our original function. So take a minute to do that on my calculator. And it looks like it's about negative 39 if I round. And then I also have an inflection point at 2, and if I plug in 2 to my original function to get the y value, that's actually going to be 2, 0. So here's all the information I need to graph, and let's see, I've got some pretty big y values, so I will scale my y-axis by 6. I will keep x at a scale of 1. Y-intercept is at 0, negative 24. So that's going to be actually at negative 4 on the y, because each y mark represents 6. An x-intercept at positive 2 and an x-intercept at negative 3. The other points on my graph, I have a minimum at negative 7/4, so that's a little bit before negative 2. negative 66, which will be a little bit off of our graph since it's scaled by 6. No maximums. 2 inflection points. One is at 2, 0. The intercept we already graphed. The other one is at negative 1/2, negative 39. So let's see. Negative 39 is going to be between negative 6 and negative 7. So about right there. Okay. And then we know that it's going to start off decreasing until the negative 7/4, and it is going to start off being concave up. So it's going to look something like this, and then it's going to change to concave down, and then go back to concave up. So this will be the general look of our graph. Should be concave up on this first piece, concave down on the second, and then concave up on the third right here. All right. So that's putting everything we've been doing for the last 3 weeks into play just by graphing the actual graph of the function.